Welcome back, guys. Today we are in ECE 2100 here at U of H, and we are working on lab number 4. This is the lab dealing with transient response for RC circuits. So first things first, let's get familiar with our circuit, with our components. This right here is our signal generator. This will be slightly different than the one you're using in the lab. However, the function will still be the same. You'll want to input the same values as it asks for on the lab. So this will include the starting value of 0 and the high value of 5 with a 2.5 volt offset and a 50 hertz frequency. So once you input all of that information into your signal generator, we are going to want to connect our signal generator. So this is what we call a BNC cable. In this case, this is our BNC to male, female, or positive, negative. And to do this, we are going to take our BNC and insert it into our coupling for our signal generator, and we're going to turn it about a quarter way through. This will ensure that our connection is stable. So now that it's connected, you can leave your signal generators off. If you look in your output, you'll see a green button, and if it shows up as green, then you'll want to hit that button to turn it off. So next things, we are going to be looking at our oscilloscope. The function generator creates our function in order to allow us to see our signals. The oscilloscope uses that function and then sees your change in inputs. So for that purpose, we are going to be using something called a probe. Now, you might not use these for this lab, however, later in the next lab, you will be using these for lab 5. So for now, these probes will serve the same purpose as this BNC connector. So we are going to connect these probes in the same way. So for your lab, in the current lab, there is a port of 3 BNC connectors up above your, I believe, function generator, and you're going to connect your input of your function generator to that port, and then you're going to connect that port down, one of those other ports down into your circuit, and then one of those other ports into your oscilloscope. And then from your oscilloscope, you're going to take your output cable and then connect that there. If you have questions on this, ask one of your TAs and they will be there to assist you. So now let's start hooking up our circuit. In front of me is our RC circuit, your circuit 1. So we have just a standard resistor and capacitor, and we are going to measure our time constant across that. So first we'll take our connectors from our signal generator, and we're going to hook it up to the very front of the capacitor, the positive lead, and the negative lead of our resistor. Refer to the first circuit in your lab manual on lab number 4. Now next, in order to measure that signal, you would generally have your BNC to BNC connector from your bus of 3 ports going to your oscilloscope, and it will automatically see that. However, for the purpose of this one, we are going to show you how to do it as a more rudimentary way. So the way we're going to use it is we're going to take our oscilloscope input lead, we're going to hook it up to the exact same nodes. Now that it's hooked up, then we should be able to see some sort of signal on our oscilloscope. As you can see, we have our signal, and I forgot to mention, but it's supposed to be a square wave whenever we measure time constants. So we have our input signal, which is basically the same signal that we measure from our function generator. The function generator should give us the same values as we should be seeing on the oscilloscope. Now, in order to measure our output signal for this circuit, we are going to take our second probe, and we're going to hook it across the resistor. So for this, we're going to hook it to the positive of the resistor, and then we're going to take our negative lead and hook it to the negative side of the resistor. All these black leads should be your negatives, and that should be what you're hooking onto the ground, or 0, depending on what you want your reference point to be. Now let's take a look at our oscilloscope. We see a very interesting curve. So if we auto-scale this, you'll see a button generally in the top right, and then that will be your auto scale. You hit that in order to auto scale it, in order to see your signal. You might have a signal like rushing by like crazy, and that's when you want to hit the auto scale to actually see the signal properly. So you should obtain some sort of signal like this. Note yellow is our input, while pink is our output. So we see this weird curve that goes up and it also goes down. So what is this curve? First of all, the x-axis of the oscilloscope this way will be measuring in terms of time, while the y will be measuring in terms of voltage. So this means that we are seeing something basically discharging and charging up towards some sort of equilibrium. This will be our RC, this is our voltage level across our resistor in this case, because our capacitor, when we work in square waves, is constantly charging up and discharging. So now let's try to find our tau, our time constant. So in your lab notebook, you'll see something called the 3/8 5/8 rule. This is derived from e to the -1, which would give you about 0.36, which is very similar to 3/8, which is 0.375, I believe. So to do this, to find our tau, we can turn off our input signal since we don't need that. As you see, this is our signal running. So we are going to turn this and make it stop by changing my source. You won't have to do this. This is only for this oscilloscope. However, because this is due to your oscilloscope in the lab automatically doing this function for you. So we are going to want to expand this. We want our top parts to be at the very, very tippity top. We want to expand our thing all the way to the extreme, and we're going to push it down as it goes. So we want our top line to touch the top, our bottom charge to touch the bottom. So you'll have to turn your verticals and move your position down as I am doing. And then you want it to be to the very, very extreme. I think that's good enough. So now from there, we want to expand our horizontal. This will give us a better look to see what our time constant could be, since if you expand x, then you can get a better overview. So now we're going to use our cursors in order to move these things. So first, this is my cursor, you can see it moving. You want to put this at the start of your charge graph. So this is basically our reference point. So since this is start, you want to line it up right when it goes to ground and then jumps up, that's where you want to line it. Then we're going to switch over to my second cursor. And then we want to use our 3/8 rule. So the divisions on the oscilloscope is divided into 8s. So each box will be 1/8. So you want to count up 3 from the bottom because this is a discharge. Versus on a charge graph, you want to count 3 from the top, so you get your 5/8 rule. So right about there, we can see that our intersects of our 3/8 line and our discharge. And then from there, we can look up here to our delta x. For your delta x in the lab, I believe it'll be located somewhere in this region of your oscilloscope screen. And we'll get our time constant of 1.06 milliseconds. Note, this time constant will most likely be different than the ones in your lab because we are not using the same capacitors and resistors as you are in the lab. And as you know, that time constant is made up of RC. So whenever you change a resistor or a capacitor, then your time constant will change. So that's how you get your time constant. And then if this is only for circuit 1, for circuit 2, then you will create that configuration and then measure across that. However, you'll still use the same principles as you use in circuit 1. That is all for lab 4. Happy data collection.